a brief revision from the previous lesson. So Bronsted-Lowry acids and base is based on the H+. If H+ is donated, or it can donate a proton, then it's an acid. If it can receive or accept a proton or H+, then it's a base. Okay, so every acid and every base will have its conjugate or its partner. So for example, if I'm looking at HCl, it's an acid, so it can donate a H+. After it has donated a H+, the Cl-, that is the conjugate base. So if I started off with a CH3, COOH, after it has donated a H+, it'll get CH3, COO-, that's its conjugate base. Okay, what about a base? For example, if I have ammonia. So ammonia has a lone pair of electrons. It can receive a H+. So after it has received a H+, NH4+ is the conjugate acid. So this is a base. Or another example, say OH. OH- can receive a H+. So when it receives a H+, it becomes water. So this is the conjugate acid, and this is the base. Okay, so that's the way Bronsted-Lowry defines acids and base. Every acid will have its conjugate base. Every base will have its conjugate acid. Some things can be an acid and a base at the same time. So before this, you learned that as amphoteric. Amphoteric means it's an acid and a base at the same time. But amphiprotic is a little bit more specific. Amphiprotic is an acid and a base at the same time using the definition of Bronsted-Lowry, meaning it can receive a H+, it can also donate a H+. For example, what are amphiprotic? Like H2O. So H2O, if it donate a H+, as an acid, it donate a H+, its conjugate base will be OH-. And if as a base, it can receive a H+, after it has received the H+, its conjugate acid is H3O+. So water is amphiprotic. Okay, so for example, if I want to write the conjugate acid or base for one of these, let's say this one, this is amphiprotic. So if I treat this as an acid, it will have a conjugate base. So if it's an acid, it will donate a H+, its conjugate base will be SO4, 2-. And it's conjugate acid. So meaning if I treat it as a base to receive a H+, after it has received the H+, is its conjugate acid, that will be H2SO4. Okay, acid reactions. So acid like HCl, they can react with metals, base, and also carbonates. So I'm just going to write one reaction for each. So a metal, Mg, can react with acid and it's going to form H2 gas. To balance it. Okay, so this is the reaction for Mg with acid. You will get salt and you get H2 gas. So remember, I reminded you this was a redox reaction because Mg here was the 0 oxidation number and this was +1, but here Mg is +2 and H2 is 0. So Cl- here is just a spectator. If you're writing the ionic equation, then eliminate the Cl-. We won't need that. Okay. Acids plus base, the most simple one, NaOH. So that's the one that you've always seen since Ig till now. Ib, still the same thing. HCl plus NaOH is acid and base. You'll get salt and water. Okay, there's no redox here. All of this is in the same oxidation state in the beginning and the end, but there are some spectators here. So Na plus is still Na plus. Cl- is still Cl-. If I were to write the ionic equation, it will be OH- and H+. I will get water, and this is also like enthalpy change of neutralization. So it's going to give me -57 approximately, exothermic. Okay, the other one would be with carbonate. So if I have NaHCO3 with acid. Okay, so if I have a carbonate here, I'm going to get carbon dioxide for sure. I'll get water. And what's my salt? So I have Na and Cl. Okay, so H and H, it went here. One of the Cl went here, and Na went here, and the carbonate went here. One of the O went to the water. So when you react acid with a carbonate, you're sure to get carbon dioxide as one of the product. Writing equations to form the following salts. So I'm just going to show this one. So this is from a propanoic acid, so CH3, CH2, COOH. This was an organic acid. Okay, so this is an organic acid plus a strong base, NaOH. So acids plus base, you'll get salt and water. So CH3, CH2, COO. And A, that's the salt, and this will give you water. From the previous lesson, you learned about pH. So what's pH? It's negative log concentration of H plus in mole per dm cube. So a change of 1 unit of pH represents tenfolds of change in the concentration of H plus, the protons. Okay, so if you have a 0.1 mole per dm cube H plus solution, you're going to get pH 1. And if you have a 0.01 mole per dm cube H plus solution, you're going to get pH 2. So you're just going to, you just need to negative log that to get the pH. Okay, the next one was water. Water can ionize slightly. So water will ionize to H plus and OH minus equally. And if it's just water in normal room temperature, you will get 1 times 10 to the power of negative 7 of H plus and 1 times 10 to the power of negative 7 of OH minus. Okay, so in IB syllabus, we will have no units for the KW because it's a comparison, it's relative, so it's being cut off. Okay, so if you look at this equation, you'll notice that it's something like the reverse of enthalpy change of neutralization. It's the other way around. So enthalpy change of neutralization, remember, you'll get approximately exothermic 57. So this will also get approximately positive 57 or 58. It's approx, okay, somewhere there. Okay, so if it's normal water, H plus is 1 times 10 to the power of negative 7. Let me be a little bit more precise here. So this multiply this, I'll get 1 times 10 to the power of negative 14. And this is fixed at room temperature, 298 Kelvin or 25 degrees Celsius. So this is our room temperature. So pure water at normal room temperatures will give you Kw of 1 times 10 to the power of negative 14. Okay, so what's the pH of water then? So pH, we only need the H plus. So just negative log the H plus. So it's negative log 1 times 10 to the power of negative 7. That will give me pH 7. Okay, so that's the pH of water, pure water. Okay, so we're not going to cover POH here because IB will not cover POH. That will be covered in other boards like A levels. Okay, examples of calculating pH. So if you have HCl with a concentration of 0.001 and HCl can dissociate fully, so I will get 0.001 mole per dm cube of H plus. So just negative log that, I'll get pH 3. Okay, what about if I get, if I start off with a base, so OH, we do need to calculate the concentration of H plus first, so this is not so direct. If I have 0.5 mole per dm cube of NaOH, I will also have 0.5 mole per dm cube of OH minus. okay, because it dissociated fully. So what I can do is to calculate the concentration of H plus, since 1 times 10 to the power of negative 14 equals to H plus multiply 0.5, which is from the OH. So what I can do is just bring the 0.5 down. Okay, so this is my concentration of H plus, so negative log that. So I think I'll get pH 13.7. Okay, let's try a question here. It's a mixture of HCl and NaOH. So we know that HCl, if you add NaOH, you'll get NaCl and water. Okay, but it's not equal now. It's 25 centimeter cubes of a 0.1 mole per dm cube HCl, but there's only 15 centimeter cubes of NaOH with the same concentration. So if you imagine that we're going to put 25 centimeter cubes of a 0.1 mole per dm cube HCl, and then I'm going to put 15 centimeter cubes of a 0.1 mole per dm cube NaOH, I'll end up to have 40 centimeter cubes. Okay, but HCl is in excess by 10 centimeter cubes. 25 minus 15, so I have 10 extra. Okay, so that 10 times 0.1 per 1,000, that will be my number of moles of H. Number of moles of H plus that is still inside here. Okay, so I'll get 1.0 times 10 to the power of negative 3 moles of H plus. Okay, this mole is in 40 centimeter cube. So 1 times 10 to the power of negative 3 is in 40 centimeter cube. I want it in mole per dm cube. So how much is in a dm cube? So using the calculator, 0.025, this will be my concentration of H plus inside this 40 centimeter cubes of mixture here. And obviously this mixture, there's an excess of HCl compared to NaOH. And this is my final concentration of H plus here. So just negative log that. Okay, so key in the calculator. And we'll get pH 1.6, which makes sense because HCl is in excess, so it should be an acidic solution. Let's look at strong and weak acids and base. So what's the meaning of strong and how is it weak? Okay, for both acids and base. Okay, strong acids and base, they will dissociate fully in a solution. So there's a picture here. So if I have HCl, I have this much of HCl. When you dissolve it in water, it will dissociate fully. So can you see all the red color H plus? So all the red ones means they have dissociated, which is 100%. All of them dissociated to H plus. So if I have 1 mole per dm cube here, if I have 1 mole per dm cube of HCl, I would have 1 mole per dm cube of H plus, and I also will have 1 mole per dm cube of Cl minus. If I have 2 mole per dm cube here, then I will have 2 mole per dm cube of Cl minus and 2 mole per dm cube of H plus, because it dissociates 100%. Okay, so strong acids and base, they will dissociate fully in a solution. So it will contain very high concentration of ions. They will conduct electricity very well. Okay, what about weak acids and base? Weak acids and base, the difference with strong acids and base. So this is not, this is different from concentrated and dilute. That's totally different from weak and strong. So concentrated and dilute, you can just alter it by adding water. But weak and strong, if they are a strong acid, they are a strong acid. If they're a strong base, if they're a weak acid, they're a weak acid. So you can't just add water or remove water to make it from strong to weak or weak to strong. If they're strong, if like HCl, it's a strong acid, means it's always a strong acid, no matter how much water you add to it. Still a strong acid. Okay, so how is a weak acid different from a strong acid? A weak acid is one that dissociates only partially in solutions. So if you look at this second picture, carboxylic acid, so CH3COOH, look at the red ones here. There's only 1, 2, 3 that's dissociated. So the rest is still in one piece. So for example, if I have 1 mole per dm cube of ethanoic acid here, I might only have, say, 0.03 mole per dm cube, for example, of H plus here. And the rest of it is still in CH3COOH, is still in one piece. So it didn't dissociate. So the ones that dissociate is just part of it. Okay, so that's what makes it a weak acid. So it's not that it's dilute. It's not that if we dilute HCl, it becomes a weak acid. No, no, no. Okay, it's still a strong acid. No matter how much water you add onto it, it just becomes more dilute. That doesn't make it a weak acid. So a weak acid is one that dissociates partially. Okay, so since it only dissociates partially, so you can see that there's less ions in that solution. So if in this picture, there's only 3 pieces that is in ions here. So that makes 6 because of the other side. So the anion as well. So 1, 2, 3, 4, 5, 6 ions only. Whereas for the strong acid, all of them are ions now. So this obviously can conduct electricity better. This one, not so well because there's so few ions in here. Remember what we learned about conjugates? So like an acid will have a conjugate base and a base will have a conjugate acid. So a strong acid is a good proton donor. Therefore, it will form a weak conjugate base. So if I have a strong acid and it donates a H+, so it's going to form a weak conjugate base. So this is a weak conjugate base. Okay, what other strong acids do we have? Say HNO3. So when it donates that H+, then you'll get NO3 minus. So this is a weak conjugate base. Okay, a strong base is a good proton acceptor, and it will have a weak conjugate acid. So the same thing here. So let's say I have KOH here. So that's a strong base, right? So sort of you'll add H+. So then you'll get K something. So if this is HCl, then you get KCl here. And then you will get water. So this here is the strong base. So this is a weak conjugate acid. Okay, so remember HCl just now? It can react with metals, and then it can react with a base. It can react with carbonates. So same goes for weak acid. The weak acid can react with the metal, base, and carbonate as well, but the rate of reaction is going to be slower. It has lower rate of reaction. Okay, let's look at this picture. So to differentiate a weak acid from a strong acid, we can see that a strong acid, looking at this circuit, the bulb glows more brightly. Why so? Because strong acids, it dissociates fully, so there's more ions inside here. And here, maybe just a few dissociated, so not so much. So in a solution like this, you can run an experiment and see that the weak acid the light bulb glows less brightly, and for strong acid, since there's more ions inside the solution, so it glows more brightly.